last time we have seen that if the principal plane has direction cosines L, M and N, then they will satisfy this set of equations and the magnitude of the principal stress is given by sigma. To determine the principal stresses, we take the characteristic equation determinant of this expression equal to 0, you could get the principal stresses by solving this set of equations. Now, the question is, how do you get the direction cosines corresponding to a particular value of sigma? You take the value of sigma, let us say sigma 1, substitute in these 3 equations, thereby you will get again 3 equations involving L, M and N. Solving these equations, you are going to get the direction cosines corresponding to the stress sigma. So, you will have 3 values of sigma out of the characteristic equation, and therefore, you can solve this set 1 thrice and you can get all the direction cosines. We would like to illustrate this by taking some example today. It is given the stresses at a point are given by this tensor, these magnitudes are all in megapascal. So, sigma xx is 12.31, tau xy is 4.20, tau xz is 0.84. Similarly, you have tau yx, tau sigma yy, tau yz, and this is tau xz, tau yz and sigma zz. Now, we calculate first the stress invariance using the data. I1 is sigma x plus sigma y plus sigma z. So, if you substitute the value, these are the 3 diagonal coefficients, it gives you 25.61 megapascal. Similarly, if you consider the second stress invariant I2, it is given by tau xy square, tau yz square plus tau zx square minus sigma x sigma y minus sigma y sigma z minus sigma z sigma x. So, this when I substitute the values, this is 4.20 this stress, then this is 5.27, this is 0.84, then we have 12.31 into 8.96, 8.96 into 4.34 and then 4.34 multiplied by 12.31. So, on simplification this will become 156.48 megapascal square. Similarly, if we try to consider the third stress invariant I3, which is given by sigma x into sigma y into sigma z plus 2 tau xy, tau yz, tau zx minus sigma x, tau yz square minus sigma y, tau zx square minus sigma z, tau xy square. So, again if you substitute the values of the respective stresses, you get this, and on simplification this will become 91.12 megapascal square. Then we try to calculate the constants. A is minus I2 plus I1 square by 3, and so if we substitute the value we have got earlier, this is minus 156.48, that is I2, and then I1 is 25.61. So, therefore, 25.61 square by 3, and on simplification this will become 6 minus 62.14 MPa square. Similarly, if we calculate the constant B, which is related to minus I3 plus 2I cube I1 I am sorry 2I1 cube by 27 plus I1 into I2 by 3, and again if we substitute the values respective values, we get the simplification to be plus 0.48. Then we calculate the angle phi. Cos phi is equal to minus b by 2 into square root minus a cube by 27, and if we substitute the values, this comes out to be a very small quantity which is almost equal to 0. Therefore, it means that phi angle is equal to 90 degree. Now, the value of the principal stress is given by sigma 1 equal to I1 by 3 plus 2 square root minus a by 3 cosine phi by 3. So, substitute the value 25.61 by 3 plus 2 square root 62.14 by 3 into cosine phi is 90. So, therefore, this becomes 30 degree, and if you simplify, this comes out to be 16.41 megapascal. Similarly, if we consider the second principal stress, it is given by sigma 2 equal to I1 by 3 plus 2 square root minus a by 3 cosine 120 degree plus phi by 3. Again, once you simplify, you get the sigma 2 stress as 0.65 MPa. If we now take the last one, it is going to be I1 by 3 plus 2 square root minus a by 3 cosine 240 degree plus phi by 3. Again, on some simplification, this is equal to 8.53 MPa. Now, at this point itself, I would like to tell you that sigma 3 can be calculated in a slightly different way, since we have the stress invariant IU1. This IU1 is equal to, it is given by sigma x plus sigma y plus sigma z, and it can also be equal to the sum of the three principal stresses. If we consider our Cartesian system to coincide with the directions of the principal stresses, so this must also be given by sigma 1 plus sigma 2 plus sigma 3. Now, we have already got the values of the two stresses sigma 1 and sigma 2, and therefore, this sigma 3 is equal to sigma x plus sigma y plus sigma z minus sigma 1 plus sigma 2. So, this can be a simpler way of going about, and if you calculate, this will also become 8.53 MPa. So, once we have got the principal stresses, now we have to determine the direction cosines. That means, we are interested in finding out what is the direction for the stress sigma 1. In other words, if we consider the direction cosines of the plane on which sigma 1 is acting is given by L1, M1 and N1, then what are the magnitude of these three direction cosines? Now, these direction cosines are going to satisfy equation number 1 that we wrote last time, and this will give us that L1 into sigma x minus sigma 1. So, we have substituted sigma by sigma 1 plus m1 into tau yx plus n1 tau zx equal to 0. Similarly, L1 tau xy plus m1 sigma y minus sigma 1 plus n1 tau zy equal to 0. Similarly, L1 tau xz m1 tau yz plus n1 into sigma z minus sigma 1 equal to 0. These three equations, once you substitute the value of the stresses, Cartesian components of the stresses, then in that case you get sigma x substituted by this. 4.20 is the value of tau yx and 0.84 is the value of tau zx. Similarly, you have the second equation here, this is tau xy plus m1 into sigma yy minus 16.41, which is the value of the first principal stress, plus n1 into 5.27, and last equation is L1 into, this is the value of tau xz and m1 into 5.27, that is the value of tau yz plus n1 into 4.34, which is the value of sigma zz minus 16.41. So, these three equations are the equations to solve for the constants L1, m1 and n1. Now, it is important to note that the three directions cosines are going to satisfy the equation which is nothing but L1 square plus m1 square plus n1 square equal to 1. So, you can make use of that, and after solving this set of equations you get the direction cosines L1, m1, n1 as 0.706, 0.628, 0.324. So, this is the direction cosines of the plane on which sigma 1 stress is acting. Similarly, for the second principal stress sigma 2, if you go by the same procedure, you will find that the direction cosines L2, M2, N2 will come out as minus 0.688, 0.519, 0.506. In the similar way, sigma 3, the direction cosines of the plane on which sigma 3 is acting are L3, M3, N3 is going to be given by 0.1525 minus 0.5831, 0.798. Now, you have got the results, you can now check it, you can check whether the direction cosines are all right. We know that the directions sigma 1 and sigma 2, they are orthogonal, and the angle between the two directions, cosine of the angle between the two directions sigma 1 and sigma 2 is going to be given by L1 L2 plus M1 M2 plus N1 N2. So, if we substitute the values that we have obtained earlier, we find that L1 L2 plus M1 N2 plus N1 L2 is equal to 4.18 into 10 to the minus 3, which is close to 0, corresponding to the values that we have got for the individual direction cosines. Similarly, you will find that for the direction sigma 2 and sigma 3, cosine of the angle is given by L2 into L3 plus M2 into M3 plus N2 into N3. This comes out to be minus 3.76 into 10 to the minus 3, which is again close to 0. So, you can now go on considering the other two stresses sigma 3 and sigma 1, and you will find that the angle between the two directions are again going to be 90 degree. So, that gives you a final check on the calculations that you have done. Now, I would like to show you that it is possible to consider, it is possible to prove that the principal directions are mutually orthogonal. You have just now seen that the principal direction cosines are such the angle between the two directions are 90 degree. Now, we would like to show it as a general case. So, let us consider the proof for principal directions are mutually orthogonal. Let us consider that sigma 1 is the principal stress 1 and the direction cosines are L1, M1, N1. Similarly, sigma 2 is the second principal stress and the direction cosines are L2, M2, N2. Now, we have the equations which we have written little while ago, that L1 into sigma x plus M1 into tau yx plus N1 into tau zx minus L1 into sigma 1 is equal to 0. So, that is the first equation. Similarly, we will have L1 into tau xy plus M1 into sigma y plus N1 into tau zy minus M1 into sigma 1 equal to 0. Similarly, we will have the third equation, L1 into tau xz plus M1 into tau yz plus N1 into sigma z minus N1 into sigma 1 equal to 0. So, for the first principal stress, we will get this set of equations. Similarly, if we write the set for the second principal stress, it is going to be like this: L2 sigma x plus M2 tau yx plus N2 tau zx minus L2 sigma 2 equal to 0, again L2 tau xy plus M2 sigma y plus N2 tau zy minus M2 sigma 2 equal to 0, and the last one L2 tau xz plus M2 tau yz plus N2 sigma z minus N2 sigma 2 equal to 0. So, now we have two sets we like to multiply this equation by L2, this equation by M2 and this equation by N2, and we would like to add these three equations. Then we multiply this equation by L1, this second equation by M1 and this equation by N1. Again we add up these three relations, and then the resultant out of this sum is subtracted from the sum that we have got from this. So, you will find that we are going to have terms like L2 L1 sigma x, here also it is going to be L1 L2 sigma x. So, therefore, this term will cancel this one. Similarly, L2 M1 tau yx, and you will find here we are going to have L2 M1. So, therefore, you will now find L2 M1 tau xy, because tau yx is equal to tau xy. So, all these terms are going to cancel. However, you will find that the term that we are going to get L2 L1 sigma 1, it is not going to cancel. So, also M2 M1 into sigma 1, they are not going to cancel. So, the terms which are going to come out of this and also of this, they are not going to cancel, and you will find that the term here is L1 L2 sigma 1, here also L1 into sigma 2. So, you can immediately appreciate that by this process we are going to get relation like this. It is sigma 2 minus sigma 1 multiplied by L1 L2 plus M1 M2 plus N1 N2, this is equal to 0. We know that these two principal stresses are distinct and they are different. Therefore, sigma 1 is not equal to sigma 2, and this equation, or rather this expression, has got to be 0. So, this gives that L1 L2 plus M1 M2 plus N1 N2 is equal to 0. This means that cosine of the angle between the two directions, between the two directions sigma 1 and sigma 2 is equal to 0. So, sigma 1 and sigma 2 directions are mutually orthogonal. By similar approach, you can again show that cosine of the angle between the direction sigma 2 and sigma 3 is equal to 0. Therefore, sigma 2 is orthogonal to sigma 3, and again cosine of the angle between the directions sigma 3 and sigma 1 equal to 0, and therefore, sigma 3 is orthogonal to sigma 1. Thus, the three directions are mutually orthogonal. So, what it means is that your two directions, any two directions, if you consider that the direction cosines are Lj1 and the other direction is Lj2 and the third direction is Lj3, then these three directions are going to be always mutually orthogonal. Now, these expressions that we have written, it has taken more space to write. We can write in tensor notation, then it will be much more compact. Now, let us consider again that this sigma 1 is the principal stress and the corresponding direction cosine is going to be given by Lj superscript 1. Again we have sigma 2 and the corresponding direction cosines are Lj superscript 2. Now, the equations that we had obtained involving the principal stresses, they were of the form we had written earlier, that Lj sigma ji minus Lj sigma delta ji equal to 0. So, now for the stress sigma 1 we can write that this is nothing but Lj1 sigma ji minus Lj1 sigma ji sigma 1 equal to 0. So, this is the set we get from the principal stress sigma 1. Similarly, for the principal stress sigma 2, without any difficulty you can write that Lj2 sigma ji Lj2 delta ji sigma 2 equal to 0. Now, we will like to multiply this thing by Li2, this equation, and this equation by Li1 with the understanding that I is also varying from 1 to 3. Then, having multiplied, if we subtract this resultant equation from this, you will find that you are going to get this terms cancelling, only these terms are going to be not cancelling, and at the same time only when we have I equal to j we will get some value, and therefore, by simplifying this what you are going to find is this L1 into superscript 1, L1 into superscript 2 plus L2 into superscript 1, L2 into superscript 2 plus L3 into superscript L3 superscript 1, L3 superscript 2. So, this is the term which we are going to get out of this multiplied by sigma 1 minus sigma 2 equal to 0. Again you find that this is nothing but, according to our earlier expression, it is L1 L2 plus M1 M2 plus N1 N2. So, this is the advantage of using tensor notation, you get very compact relationship. Now, we would like to show that the principal stresses are real, they are not going to have complex quantity, since the equation that we had gotten by writing the characteristic equation, it was nothing but sigma cube minus I1 sigma square minus I2 sigma minus I3 equal to 0. the roots of this equation are going to be all reals. So, this equation, if we indicated as equation number, let us say 3. So, roots of equation 3 are all real. Let us assume that the 3 roots are again sigma 1, sigma 2 and sigma 3. Let us consider that sigma 3 is real, but sigma 1 and sigma 2 are complex. Since I1 is equal to sigma x plus sigma y plus sigma z, this is a real quantity, and at the same time we have seen that this I1 is also equal to sigma 1 plus sigma 2 plus sigma 3. If the sum of these 3 quantities have got to be real, it demands that sigma 1, sigma 2 must be related. In fact, one should be the complex conjugate of the other. So, if sigma 1 and sigma 2 are complex, to get the imaginary part of this sum of these 2 roots to cancel, we must have sigma 1, sigma 2 must be conjugate, complex conjugate. Sigma 1 and sigma 2 are complex conjugates. Now, you would also recollect that the equation that we are going to be satisfied by these are Lj sigma ji minus Lj delta ji into sigma equal to 0. So, this is what is the equation to be satisfied by these roots. Now, we find that this component is complex, one of the component is complex, and therefore, this equation now going to involve complex coefficients, and hence it will indicate that the direction cosines have got to be complex. So, sigma 1 and sigma 2 are complex conjugates, and then this equation is to be satisfied by all the roots. Let us write that the direction cosines corresponding to sigma 1 is Lj superscript 1. Similarly, for sigma 2 it is Lj superscript 2. Now, this equation we will have for each Lj 1 sigma ji Lj 1 delta Ji sigma 1 equal to 0. Similarly, Lj 2 sigma Ji Lj 2 delta Ji sigma 2 equal to 0. Now, these two equations A and B, these are all real quantities, and here this is complex. So, also in this equation this is complex. So, we are going to get a set of equations involving complex coefficients, and it is natural to expect that this Lj and Lj1 and Lj2 roots of these two equations must also be complex. So, Lj1 and Lj2 are complex. That means, if Lj1 has components like L1 1, M1 1, N1 1, we can write simply, we can write this thing as L1, M1 and N1. Then each of these components must be complex. So, this could be that L1 is of the form A1 plus IB1, M1 is equal to C1 plus ID1, and this is, let us say, E1 plus IF1. Now, if we try to take the equation 1 and take its complex conjugate, so if we try to take complex conjugate of A, so it will look in this form Lj1 bar sigma Ji minus Lj1 bar delta Ji sigma 1 bar is equal to 0. So, that is the complex conjugate form of equation number 1. Now, this sigma 1 bar is nothing but sigma 2, that is the stress sigma 2, because sigma 2 is complex conjugate of sigma 1. So, equation A dash, it now comes out to be of this form Lj 1 bar sigma Ji minus Lj 1 bar delta Ji sigma 2 equal to 0. So, that is the form of A dash. Now, this is a equation which is involving sigma 2 here. So, it is natural to expect that if you compare now these two equations, A, B and A dash, C, it is natural to expect that these two must be related. So, this means that Lj 1 bar must be equal to L2, I am sorry, Lj superscript 2. So, therefore, this comparison gives us that Lj 1 bar is equal to Lj 2, and hence Lj 1 and Lj 2 are again complex conjugates. Now, we go back to equation number A and B. From A and B, if we again multiply this equation by Lj2 and this equation by Lj1 and subtract. So, if we do the subtraction, so from A and B, we are going to get Lj1 Lj2 minus sigma 1 multiplied by sigma 1 minus sigma 2 equal to 0. So, this is equation C. So, therefore, we just consider these two, consider multiplying this thing by Lj 2 and this by Lj 1 and subtract the resultant equation out of here from the resultant equation from there, that will give you this. Now, if we assume that sigma 1 is equal to alpha plus I beta, since it is complex, and since sigma 2 is complex conjugate of sigma 1, therefore, sigma 2 can be written as alpha minus I beta. So, from C now, what we have is Lj 1 Lj 2 multiplied by 2I beta equal to 0. Now, since Lj 1 and Lj 2 are complex conjugates, and we can write the coefficients of the, since we can write now the coefficients of Lj 1 as A1 plus IB1 and the components are this is C1 plus ID1 and this is U1 plus IF1. Similarly, Lj2 components are, since they are complex conjugates, so therefore, it is going to be IB1 C1 minus ID1 and this is U1 minus IF1. Now, these A1, B1, C1, D1, U1, F1, they are all real. So, start A1, C1, E1, so also B1, D1 and F1 are all real quantities. So, now Lj1 into Lj2 should be equal to nothing but this multiplied by this plus this multiplied by this plus this multiplied by this. So, it is nothing but L11 L12 plus I am sorry, it is L21 L22 plus L31, L32. So, this will give us A1 square plus B1 square plus C1 square plus D1 square plus E1 square plus F1 square. Now, this expression is always some positive real value. So, from equation C now, from equation C that we have, it is quite clear that beta, this product is real and this 2I beta is equal, product is 0. So, therefore, this is real and this simply means that beta has got to be 0. So, this relation indicates that beta is equal to 0, and we assume that sigma 1 equal to alpha plus I beta, sigma 2 equal to alpha minus I beta. It simply means that sigma 1 and sigma 2 cannot be complex. So, the roots of the characteristic equation involving the principal stresses are real. So, roots are thus we can show that the other roots are also going to be real. You can now consider solving some problems yourself. You consider this example, prove that S1 by sigma 1 square plus S2 by sigma 2 square plus S3 by sigma 3 square equal to 1, where SI is R, the traction on an arbitrary plane through the point P with principal stresses sigma I is. So, this sigma 1, sigma 2, sigma 3 are the principal stresses at a point P, and S1, S2, S3 are the tractions on an arbitrary plane inclined with the three principal directions. Prove that this relation is equal to unity. Second example, you can consider determination of principal stresses and their direction cosines, where the stresses in Cartesian coordinates are given by this expression 0, 100, 100, 100, 0, 100, 100, 100, 0 MPa. And the answer for this case is going to be sigma 1 equal to sigma 2 equal to minus 100 MPa, sigma 3 equal to 200 MPa, and the direction cosines connected with the sigma 3 stress is 1 by root 3, 1 by root 3, 1 by root 3. Similarly, determine the stresses sigma and tau on a plane which is equally inclined with the three Cartesian axes, and here the stress tensor is given by 100, 100, 100 MPa, 100, minus 50, 100 MPa, 100, 100, minus 50 MPa. And this answer for this case, the normal stress is given by 200 MPa and the shear stress is 70.7 MPa. You can consider the fourth example. You write the stress invariance in terms of the principal stresses sigma I. That is, you write the expressions for I1, I2, I3 in terms of the principal stresses sigma 1, sigma 2 and sigma 3. I would like to consider the solution for this example 4. So, example 4, we have I1, it is directly related to the 3 principal stresses and their sum is going to give you the first stress invariant. Now, second stress invariant, I would like you to consider the relationship we had tau xy square, tau yz square and the third component minus sigma x, sigma y plus sigma y, sigma z plus sigma z, sigma x. Now, in this case the shear stresses are all 0 since we are working in terms of the principal directions. Therefore, we are going to get directly sigma x to be sigma 1, sigma y to be sigma 2 and therefore, this is given by minus sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Similarly, the third stress invariant is given by sigma x, sigma y, sigma z plus 2 tau xy, tau yz, tau zx minus sigma x into tau yz square minus sigma y into tau zx square minus sigma z into tau xy square, and since in this case shear stresses are all absent and the sigma x is nothing but sigma 1, this is sigma 2, this is sigma 3. Therefore, the third stress invariant is given by product of the 3 principal stresses sigma 1, sigma 2 and sigma 3. So, the 3 stress invariants are going to be very simple expressions. I1 is sum of the 3 principal stresses, I2 is nothing but minus product of the 2 principal stresses taken in succession and I3 is nothing but product of the 3 principal stresses.